Hey everyone, welcome back. If you've ever wondered how machines turn words into math, you're in the right place. In the next 5 minutes, I'll walk you through the main types of embeddings in NLP, when to use each one, and practical tips so you can pick the right approach for your project. Let's dive. First, what exactly is an embedding? Simply put, embeddings are numeric vector representations of discrete items, like words, subwords, sentences, that capture semantic information. Think of it as placing words in a space where similar words sit close together. We'll use everyday analogies and visuals to make this concrete. Why do embeddings matter? They power search, recommendation, translation, question answering, and many NLP systems by turning language into numbers that models can reason about. Good embeddings improve generalization, reduce feature engineering, and enable similarity searches, which are huge in production systems. Let's start with the basics. One-Hot and count-based embeddings like TF-IDF. One-Hot encodes each token as a vector with a single one, very sparse. TF-IDF weights tokens by importance across documents. These are simple and fast, but they don't capture semantic similarity between different words. Next up, dense word embeddings. Think word-to-vec and glove. These produce low-dimensional continuous vectors that capture syntax and semantics. Word-to-vec uses a predictive model, skipgram or CBOW, while glove uses global co-occurrence counts. Both create embeddings where king minus man plus woman equals queen works surprisingly well. Dense embeddings are great, but they assign a single vector per word. Contextual embeddings like Elmo and BERT give different vectors depending on surrounding words, capturing polysemy. BERT uses transformers and attention to build deep contextualized token representations. This was a game changer for many downstream tasks. How do models handle rare words or misspellings? Enter subword and character embeddings, byte pair encoding, word piece, and character CNNs or LSTMs. These split words into smaller units, so unseen words can still get meaningful representations from known subwords. Word-level embeddings are great, but many tasks need sentence or document-level representations. Traditional approaches include averaging word vectors or doc-to-vec. More recently, models like sentence BERT produce high-quality sentence embeddings suitable for semantic search and clustering. Working with multiple languages? Multilingual BERT, Laser, and Muse map different languages into a shared space, so semantically similar sentences align across tongues. This enables cross-lingual search and transfer learning, very useful when labeled data is scarce in a target language. How do you evaluate embeddings? Popular metrics include cosine similarity for retrieval, intrinsic tests like word analogy and similarity benchmarks, and extrinsic evaluation by measuring downstream task performance. Remember, the best embedding depends on your task and data. Practical tips: use pre-trained embeddings when you can, but fine-tune for your domain if you have labeled data. Watch out for vocabulary mismatch, out-of-vocab tokens, and dimensionality trade-offs. Higher dimension isn't always better. For production, consider memory, latency, and whether you need static or contextual embeddings. Let's walk through a quick pipeline. You take raw text, tokenize with subword tokenization, feed into a contextual encoder like BERT, extract embeddings, token or pooled sentence vector, and use them in a classifier or similarity search. I'll summarize the commands conceptually so you can try it locally. What's next? Expect more efficient contextual models, distillation, adapters, better multilingual alignment, retrieval-augmented models that combine embeddings with external knowledge, and multimodal embeddings that join text with images or audio. The field is moving fast. Stay curious. Quick recap. One-Hot and TF-IDF are simple baselines. Word-to-vec glove gives static dense vectors. Contextual models like BERT give context-aware vectors. Sentence embeddings power semantic search. And choose embeddings based on your task constraints. If you found this useful, hit like, subscribe, and check the description for links to code, papers, and a cheat sheet. See you in the next video.